You are welcome to Day 2 Academy, where we're devoted to building excellence in students, especially when it comes to the STEM subjects. Our video today is going to be of great help for you if you are preparing for your physics exam, particularly talking about WAEC, GCE, NECO, GED, GCSE, IGCSE, and Co. And we are going to be using the NECO 2021 Physics Theory Paper as a guide in this particular question set. We are going to be looking at all of the questions that are featured in that exam in a bit to help prepare you for excellence so that you can be the best that God had created you to be. Now, there are so many other videos that are available from our channel, so you can just check them out, look at resources on mathematics, physics, chemistry, so that they can be of help for you to be the best and gain that excellence that you are longing for. If you are here and you are watching this video, we'll appreciate that you just take a moment to go ahead and subscribe to the channel. Just click on the subscription icon and also click on the notification bell so that you get notified of our video resources once we upload them. It's free of charge, and that is our little contribution to actually make the world a better place. So our work is set out for us. Let's just go ahead and delve into our video together. Here in our very first question, we're asked to mention a device used for detecting fault in electric circuits, and then we have to mention one feature of the named device in A above. So I would love to actually mention a multimeter, or what some other people call an avometer. Okay, that is quite good. Or you can actually use a simple continuity tester. The difference is that the continuity tester will only check if there is no breakage in, let's say, a conducting wire. So you put one end of the wire here and you put the other end there. Sometimes those devices, they just give beep sound to show that there is actually no breakage on the connecting circuit. And a multimeter or an avometer can also do that, but in addition to that, it can also measure so many other things. Maybe you can get to measure your current, your voltage, your resistance value, and that's why you are seeing that there are many divisions here. So you can just switch to whichever one is suitable for what you want to measure, and that is as good as it gets. Now, some of the features, of course, it will need a connecting wire that's shown in red and black here. And here you are going to have a display. This is actually an analog display, but some do come at digital display, in which it digitizes the result of whatever it is you are measuring. And then another thing you need for them is a powering cell for you to power the device as appropriate. So that is the answer to this question, and we are good and fine with it. This question is requesting us to distinguish between simple and compound microscopes. Okay, this is just a pictorial view of what this can look like. And in a simple microscope, we have only one converging lens as opposed to two converging lenses in the compound microscope. The simple microscope has low magnification, whereas the compound has a very high magnification, so you can see a bigger and an enlarged image of what you are looking at. And then in the simple microscope, the final image is erect, whereas in the compound microscope, the final image is inverted. So you can just pick a combination of two of these and you get your full marks. Note that you are not requested to draw a diagram, but for us, we know a picture is worth 1,000 words. So showing you will actually engrain this more on you so that you will be able to recollect better if you are in your exam hall. All right. Here we are told that the mass of copper deposited on the cathode of a copper voltammeter is 450 grams when the current passed through it for 25 minutes. Our mandate is to calculate the current passed through the voltammeter, and we are given the electrochemical equivalent of copper to be 3.33 exponents minus 4 grams per coulomb. So here we are going to be making use of Faraday's law of electrolysis, which is estimating that the mass deposited in such a setup is proportional to the quantity of electricity that is passed through it. And for us, in this particular case, since we are having current, we can say that means that inherently the mass is proportional to the current passing through it and the product of time. So if you bring in the constant of proportionality, that's where we have our electrochemical equivalent Z multiplied by IT, such that in this particular case, what we are asked to find is the current passing through the voltmeter. Okay, current passing through the voltmeter will now be the mass divided by electrochemical equivalent multiplied by T. All right. So if we just want to do that with all the values that we have been given, we have the mass deposited as 450 grams. We have the electrochemical equivalent, and then the time was given in minutes. We need to convert that to seconds. So we can say the current in this particular case will be the mass 450 grams divided by the electrochemical equivalent, which is 3.3 times 10 raised to the power minus 4 grams per coulomb. Okay, multiply by the time. The time is 25 minutes, so that is 25 minutes, but we need to convert to seconds, so we can say multiply by 60 seconds. So we just need to bring in our calculator to solve for this. That 450 divided by the product of 3.3 exponent minus 4 multiplied by 25 multiplied by 60. Okay, just ensure that you put in everything correctly, and then we can look at that. This is 10,000 over 11, but in standard form 909.09, so this is 909.09. the dash on it means that it's repetitive, and we can just say this is nothing but 909.1 amperes. That is the current that is passing through the voltmeter. Okay, in this question on friction, we are told that a wooden block was placed on an inclined plane as shown below. So this is a wooden block that is placed on this inclined plane. Okay, now if it is just about to slide, we have to show that the ratio of the sine of angle phi, this angle phi, to the cosine of angle phi, okay, is the same as the coefficient of friction. All right, now if we want to just prove that, we know that normally the coefficient of friction is the force over the reaction that is being experienced on that particular wooden block. And in this particular case, if you are to look at it, if this angle here is phi, and we are just to construct our angle something sort of this, we can see that this angle also is phi because it's corresponding to this. So this angle here and this, they are corresponding angles, and that being the case, this particular f and r, we can resolve them along this phi. In short, let me just move this so that we'll see this clearly. So in moving that, this is exactly what it's looking like, and if you want to resolve it, we know that we can get to just resolve this on the horizontal and the vertical component, and in that particular case, we'll see that the force upward to the plane will be given as mg sine alpha, okay, because alpha is the angle of inclination of that f to the horizontal, so it will have to be sine alpha. You can just recollect your SOHCAHTOA. If you just recollect SOHCAHTOA, you can easily work that out, okay. And then in the same vein, r that we are looking at will be mg cos alpha. Now, where is mg? Mg is actually the weight of the block acting downward. So if that is the case, our coefficient of friction, we can say, is nothing but f, which is mg sine alpha, over r, which is mg cos alpha. Okay, so we can see that already mg will cut out, such that the coefficient of friction is nothing but the ratio of the sine of alpha to the cosine of alpha. Of course, that is tan alpha, but this is what we are asked to actually prove, and that has been shown as appropriate. In this question on projectiles, we are first asked what is the range of a projectile, and then we are being told that an athlete threw a javelin with a velocity of 12 meters per second. If the javelin hits the ground after 1.5 seconds, we have to calculate its angle of projection. Now we have to take the acceleration due to gravity g as 10 meters per second square. In the first case, the range is the horizontal distance from the point of projection of a projectile to the point where the projectile hits the projection plane. So for this particular diagram, that range will be defined here. So this is actually that range that we are being asked to define. And then in the second vein, we are to look at this particular case scenario in which the athlete is throwing a javelin with an initial velocity of 12 meters per second, and then the javelin will hit the ground 1.5 seconds later. We have to find the angle of projection. Now, for us to look holistically at this question, let's consider the upward movement of this particular projectile. Okay, for that upward movement, we know that generally time for it to reach maximum height, since we are only talking about the upward movement, we can get by making use of v is equal to u plus at. Now, since we are talking about the upward movement, we know that at the maximum height, the v is actually 0. Okay, the u, which will be the vertical component of its initial velocity, will now be u sine theta. Okay, theta is the angle of inclination, right? Then the acceleration due to gravity, because it's going upwards, that's going to act in the negative direction, so it will be minus g, not just a, it's minus g, then multiplied by our t. So from here I can say the time for it to reach maximum height is nothing but U sine theta over G. But then, since it's actually a two-way journey, it will go up, but it will also come down. Okay, that means the total time of flight T will be 2U sine theta over G. I know this is a formula that is quite popular with students. I just took my time to explain it out because it's going to help us now to try and solve our question as we are given here. Okay, so yeah, we have already been given the time. Now we are looking at 2U sine theta over G, and what we are looking for is actually theta. So we can make sine theta the structure of the formula. So that means we can say sine theta is nothing but the total time of flight multiplied by G over 2 multiplied by U. Okay, so if we want to put in our parameters, that means we are saying that it is the total time of flight was given as 1.5, G was given as 10, 2 multiplied by the initial velocity will be 2 times 12. Okay, that means that sine theta is equal to, this will be 15 over 24, 15 over 24, and then theta itself will be arc sine 15 over 24. So this is what we need to put into our calculator to get our solution out. We want to say arc sine 15 divided by 24. Okay, so we can close our bracket. What's that going to give us? That is 38.682. So we can say theta itself is nothing but 38.682, or we can just say 38.68 degrees as our solution. So if you know the formula for the total time that it takes for the projectile, you can actually rearrange to get your sine theta and then find the arc sine to pick your final answer. But I just love working from the ground up, so that's why I just took my time to explain this. But eventually our final answer will be 38.68. all right. In this question, we are being asked to mention two bodies possessing kinetic energy, and then we are told that a waterfall is 108 meters high. We have to calculate the difference in temperature of the water above and below the waterfall. We have to take acceleration due to gravity as 10 meters per second square. Now, for the very first question, you need to know that for you to actually answer this question, you just need to consider any object that is moving at all. So, talk about a moving car, a fruit falling from the tree, a stone that is thrown, a bullet that is fired. Any one of these is going to possess kinetic energy. The velocity is what is accounting for that. And if you are able to mention two, we are good and fine. In the second case, that we are looking at a waterfall which is 108 meters high, and that is being shown in this diagram here. Now we have to calculate the difference in temperature of the water above and below the waterfall. Now this is what they are trying to ask us, that here we can have conservation of energy from the potential energy to heat energy. Once we are able to actually get this, the question will be easy for us. And we know that the formula for potential energy, in this case for this waterfall, is the mass and acceleration due to gravity times the height which the water is actually going through, and then the heat energy is given as mass multiplied by the specific capacity of water multiplied by the change in temperature. That change in temperature is the difference between the theta 1 at the top of the waterfall and theta 2 at the base of the waterfall. Okay, so we can just call that change in theta. You can see from this formula that the mass is going to cut out, and then we have GH is equal to C multiplied by the change in theta. So we have GH is C multiplied by the change in theta. So that the difference that we are asking us, the change in theta, we can obtain by saying we are using GH divided by C. And what are the parameters that we are giving? We are giving G as 10 meters per second square. We are giving H as 108 meters. We are not giving C, so you can just leave it as C. Okay, I think C is about 4,200 joules per kilogram per Kelvin. But since we are not giving, just leave it at that, and you can finally state that the change in temperature for this particular waterfall is 10 times 108 is 1080 over C. But then you do have to mention the unit, so it is degree Kelvin, or you can say degree centigrade. Is a change, so anyone will do, and you'll be fine and good. Okay. In this question, we are being asked what vaporization is, and we have to state one effect of the increase in heat for a temperature range of 50 degrees Celsius to 100 degrees Celsius on first on plastic and then on iron. Okay, very good. If you want to define vaporization, you can state that it is the process in which a substance changes from its liquid state to gaseous state at constant temperature. Student, I cannot emphasize this enough that it has to be at constant temperature. Okay, that is what will earn you your full mark. You don't just say it's a process in which substance changes from liquid to gaseous. That constant temperature just has to come in place. That is what will earn you your full mark. And then, looking at the second question, what we are being asked inherently is to consider what will happen to this particular material. Is it going to melt, or is it going to just have some changes in its properties as a reason of the increase in temperature from 50 degrees Celsius to 100 degrees Celsius? Of course, for plastic, the plastic is going to melt because that is way above its melting point. So for the plastic, it's going to melt, and then there will be change in its density. However, for iron, because that temperature is not going to be up to its melting point, it's only going to expand. And because it is also functioning as a reason of electrical resistance, it's also going to affect some changes in its electrical resistance. It will also have some changes in its density. So with this, we've been able to look at this question perfectly. This is a question on waves, and our mandate is to explain how stationary waves are produced, and then to look at this question and calculate the wavelength of this waveform that is shown in the diagram. Okay, very good and very fine. If you want to have a look at that, for the way in which stationary waves are produced, it's just by the superposition of two progressive waves that are having first the same frequency and then the same amplitude, but they are moving in the opposite direction. So like in this particular case, you are saying that this wave, this is moving in this direction and this is moving in this direction. Both of them, they are going to, they are having the same amplitude, they are having the same frequency, and then they will produce a stationary wave. And if you want to look at the waveform, now this is the amplitude and maybe this is the time or the frequency, you can see that as one is actually going on the thick, the other is going on the broken line, and the cumulative effect of the two at any instant in time will be that they will cancel out each other. So a stationary wave will be produced. So that is the answer to the first question. In the second question, you are to look at the waveform and we are to get the wavelength. Normally, wavelength is the time it takes to complete one cycle. So here, if we are looking at this, when are we going to have a complete cycle? We are going to see that from this particular origin, this is half of a cycle and this is actually a full cycle. Okay, again we have another half here, and here we have another full cycle, and then here we have another half. So what we are looking at here is that we are having 4 meters to be synonymous to this is one complete cycle, another complete cycle, and a half is synonymous to 2.5 cycles. Okay, so our question is asking us what is going to be the value of the wavelength that will correspond to one cycle. So this is what we have, and we can just say we want to cross multiply that. In this case, we have 2.5x is equal to 4 times 1, and if we divide both sides by 2.5, this is also by 2.5, we can see that here the 2.5 here will cut, then 4 divided by 2.5, what's that going to give us? 4 divided by 2.5, that's what? 8/5, which is 1.6. So x, which is the wavelength, is nothing but 1.6 meters for this particular waveform. So we just know that it is going to take a wavelength to complete a circle, but here we're having 2.5 circle, so which is 4 meters. 4 meters corresponding to 2.5 circle. We can find the length that will correspond to a single circle, and we just got that to be 1.6 meters. Okay, let's ask ourselves this question. Why is it that sound does not travel through vacuum? Okay, so that's our first question here. And then we're also being asked that when is the critical angle said to be subtended by an incident ray of light? We're also to state one of the conditions for total internal reflection of an incident to occur. Okay, all right. For the solution to these questions, in the first case, sound does not travel through vacuum because sound needs a material medium for its propagation. So since vacuum is not a medium, it cannot travel through a vacuum. Okay, so that takes care of the very first question. Now, when is critical angle said to be surrounded by an incident ray of light? It is when the ray is reflected along the boundary of a media. So here, the ray is coming initially and then is refracted along that boundary of the media. Then in that case, we are saying that the critical angle is subtended by that incident ray of light. Okay, and then one of the conditions for total internal reflection to occur, there are just actually two of them, this and this. In the first case, the ray must be traveling from a denser medium to a less dense medium. So the original source of the ray will be more dense, meaning that it's going to restrict the movement of that ray of light as compared to the other medium that light is traveling to. And then the second condition is that the angle of incidence in the denser medium will be greater than the critical angle of the medium. So once that angle of incidence is greater than the critical angle, then total internal reflection will definitely occur. All right. Here we are looking at a question in electricity. We are being asked what is lost volts and to state two advantages of secondary cell over primary cell. So this is just as good as it gets. In the first case, looking at lost volts, it is the voltage drop due to the internal resistance of a cell. So here you can see we have this particular cell. Okay, that is actually supposed to be producing the voltage V in this particular circuit, but that cell itself is having an internal resistance R. So what we are going to have is that, of course, the same current will flow in a series circuit. So the V that we are having is going to be nothing but the current multiplied by this small internal resistance of the cell itself, then plus the current multiplied by the load, the resistive load that is applied on the circuit. So what we are looking at when we are talking about lost volts is a product of the current multiplied by this internal resistance of the cell. So this is what is regarded to as the lost volt. Okay, and then in the second question, the secondary cells, actually the advantage it has over the primary cell is that first, it produces current for a longer time. You can use it for quite a longer time as compared to the primary cell. Then of course it can be recharged. So you use it, it's depleted, you charge it, then you can use it again, charge it, use it again. But for the primary cells, once you use them, that is all. You just need to discard them, or even need to discard them properly. Okay, so that is that with respect to this question. We are still continuing with our questions on electricity, and here we are to state the condition under which resonance occurs in an AC circuit. And then furthermore, we are being told that a series circuit of 5 ohm resistor, 2.3 millihenry inductor, and 0.03 microfarad capacitor is connected in series to an AC source. Our mandate is to find the resonance frequency given that pi is 3.14. Okay, so that is good and fine. Here, this is going to be the solution to our question. In the first case, resonance will occur when the inductive reactance is equal to the capacitive reactance in an AC circuit. So this second question is actually a very typical case scenario of when we have resonance, because they are asking us to find the resonance frequency. So what is happening is that at resonance frequency, SC is actually equals to XL. And what's the formula for XC? What's the formula for SL? That means we are saying that XC is 1 over 2 pi FC, okay, is equal to XL is 2 pi FL. So this, if you actually cross multiply and rearrange, we are going to get that the frequency, which is the resonance frequency, is nothing but 1 over 2 pi multiplied by square root of LC. Students, you can actually lay your hands on this and try to get the formula out. But starting from where we are coming from, the resonance frequency is actually given as this. And for this question, that's exactly what we are going to be using to say that here, what is our L? Our L is 2.3 millihenry. That is 2.3 milli means times 10 raised to the power minus 3 Henry. Okay. And what is our capacitance? Okay, that is 0.03 microfarad. That is 0.03. Micro means times 10 raised to the power minus 6 farad. So if we want to use these parameters, we can say our F is nothing but 1 over 2 pi. Pi will have been given as 3.14. Then multiply by the square root of L, that is 2.3 times 10 raised to the power minus 3. Multiply by C, 0.03 times 10 raised to the power minus 6. So you just need to capture this correctly so that you don't make any mistakes, students. With this, we can now find our resonance frequency by bringing our calculator to say we want to look at 1 divided by, I want to put everything in brackets, 2 times 3.14 multiplied by the square root of, now I want to put this everything together in brackets so that I don't miss out that square root. So I have 2.3 exponent minus 3, okay, times 0.03 exponent minus 6. So I can close that bracket, come out of that, and check to see that I'm actually on the right track, and then I can press the equal to sign. So this is 19169.72, 19169.72, okay. I can just say I want to approximate this, and if I bring this decimal 1, 2, 3, 4, okay, 4 places, I can say this is 1.92. I'm rounding up this 6 to 1 and adding to this 1, then times 10 raised to the power 4. I've moved the decimal place in 4 places, and then the unit for frequency is hertz. So that is going to be the resonant frequency for this particular circuit as given in this question. In this question, we are to mention 2 types of unit cells of a cubic crystal other than the face-centered cubic, and then we are to calculate the half-life of a reactive element of decay constant 0.0385 per second. Okay, good and fine. The other unit cells apart from the face-centered cubic is simple cubic crystal as typified in sodium chloride crystal, and then the body-centered cubic crystal. So if you just mention these two, you are good and fine with question number A. Okay, and then in question number B, we are being given that the decay constant lambda is given as 0.0385 per second. Our mandate is to find the half-life. Now, half-life in this particular case is given as 0.693 divided by lambda, and since that lambda, the decay constant, was given as 0.0385, we can just put in the value to say this is 0.693 over 0.0385 per second. So we just want to put that value there. We can make use of our calculator. 0.693 divided by 0.0385. This is 18. Okay, so this is 18, and now it's as if we are reversing this, so it will be 18 seconds as a half-life of this radioactive element. Here in this question, we are being mandated to draw a label diagram of a photocell and also mention 2 applications of a photocell. So no problem. If you want to draw a photocell, I'll just do a simple diagram here. You can have this, and typically we are going to have an anode, okay, that is going to be collecting rays of light, and then a cathode that's going to be receiving electrons from there. So I can link this to a micro ammeter, and then I can have, let's say, battery source, and just finish up like this. Okay, so normally the operation of the photocell will be that rays of light will be coming in incident on the anode. Okay, so this here is the anode, this is the anode, and then here this is the cathode. And then with those rays of light coming in, what we are going to be having is that electrons will be ionized and they will move to the cathode from the anode, and then that will complete the circle such that we can have electricity flowing in this particular case. So this is just a typical example of what we have. And here, critical things to note is that here we are going to have vacuum. This is actually vacuum, and of course this is an evacuated glass tube, so that's why inside it we are going to have vacuum. So this is just a very simple diagram of a photocell. When you are drawing, you can just represent the anode as a single line, represent the cathode as a single line. Maybe you just draw your evacuated glass tube, just do something like this, and you are good and fine. Okay, so you don't need to be too artistic if you are drawing. I just want to give a good representation for you. If you can do this, fine and good and no problem. You also be awarded your full mark. That is not a problem. So let me just straighten this up a little, okay? And then I can just include this as a glass tube, okay, which is evacuated. That's why we have vacuum in that particular. So If you can label all of this and just get it like that, you are good and you are fine. And then to look at the applications, this Photocell actually finds applications in burglar alarm, automatic door, TV camera, detection of light, measurement of light intensity. So that is that with respect to this particular question. Here we're asked to explain fundamental quantity and to measure two quantities which have the same unit as energy. As a reason of definition, fundamental quantity is any physical quantity that is not dependent on other quantities. It's a standalone quantity. It's any of the quantity from which other quantities are derived. So that's why we call it fundamental. Okay. Now, in the second question, we are being told that we are to look at two other quantities that have the same unit as energy. Okay, let's say we want to look at potential energy. Okay, we know that potential energy mathematically is given as mass translation due to gravity times h. And if that is the case, we want to break this down. We can say this is inherently mass. We can't break down to any other quantity again. Acceleration due to gravity is velocity over time. Velocity itself is, maybe you can say, displacement over time, then multiplied by 1 over t. So it's velocity over time. That is acceleration due to gravity. Then height, that is just distance, so I can call that d. So what we have here is we have m, a single m, d we have in two places, then t at the denominator, that is t raised to the power minus 2. And we want to put it as the base fundamental unit. We can say this is nothing but, for the mass we have m, for distance that is l raised to the power 2, and then for time that is capital T raised to the power minus 2. So what we are looking for inherently are two other quantities whose dimensions is going to be ml squared t minus 2. Okay, so if you want to look at that, I know that work and moment are going to give us that exact dimensions. And what is work? Work is actually force times distance. Okay, force itself is mass times acceleration. Okay, then we still have distance there. So if you want to look at the breakdown of this, you can say mass, this is just m. Okay, acceleration is velocity over time, that distance over time, which is velocity, then over time 1 over t, then multiplied by distance. I have that as d, and you can see that's corresponding to what we have here exactly, that we have it as md squared and t minus 2, which inherently will still land out as ml squared t raised to the power minus 2. So that is quite on track. Work is having the same unit as energy. We did this breakdown of the dimension for us to get that. In the same way, we can look at moment. Moment is actually turning force, so it is force multiplied by distance moving in the perpendicular direction. Like for example, you have we have a wrench. If you have a wrench that you're actually using, and then you are turning it, maybe you apply a force like this, and this is the perpendicular distance, and this is f. Moment is the product of that force multiplied by the particular distance. So eventually it will just give us something like this again, that we're having force and distance, which is mad, and eventually mad. And then that will also give us md squared t raised to the power minus 2, whose dimension will also be ml squared t raised to the power minus 2. So we can see that energy, in this case, we even use potential energy as a case study. You can use kinetic energy. Students, you can just try your hand on that. Use kinetic energy, okay, half mv squared, and then you could see that you also arrive at the same thing here, and we have found that work is also having the same, moment is also having the same. So work and moment, they have the same unit as energy. All right. Yeah, in this question, we are being told to sketch a velocity time graph of the motion of a pendulum bob which is swinging from one end to another, okay. So if you want to look at that, this is what the movement of that pendulum bob is going to be like. So maybe you can say here it's just fixed, okay, and then the bulb is swinging from left to right, left to right, left to right. Now this is what we notice. If you actually take this particular, let's say this is point A, this is point B, and this point C, what you notice is that at every point in time, the pendulum bob is tending to return to point B. Okay, so even if you are starting from B and you are going to C, you discover that it will get to a point, it will revert back to B. Then it will go to A. Once it gets to A, it will also what? Revert back to B. So generally, since the acceleration is directed to the center, to B, then that means that your velocity time graph will take a shape and look like this from here, which you can say is A. It will come here, it will peak at B, and then it will go back to C, and then it will just repeat that circle again and again. So I can call this point A, just as a reason of explaining what I have over there. I can call this point B, and I call it point C. So this is going to be the velocity time graph. The velocity will increase anytime it's pointed towards the center, towards B, okay? And once it's going away from B, the velocity will decrease. So this is actually how the velocity time graph will look like. And once you'll be able to sketch this, you'll go with the question. In this question, we're asked to distinguish between elastic and inelastic collisions. And for us to just take it on a light note, this is a pictorial view and a table list of what we are being asked. In the first case, for the elastic collision, kinetic energy is not conserved. And then the final velocity after collision is not the same. So this is U1, this is U2. If they collide, you can see that V1 and V2, they are not the same. They are still moving in some different direction as typified in this diagram, okay? So the bodies also do not stick together after collision. You can see they are going their different ways. But in inelastic collision, kinetic energy is not conserved at all in this case. And then if they are initially moving with initial velocity U1 and U2, after the collision, the final velocity after the collision is the same. They have a common V, okay? And then the bodies, they stick together after the collision. So the prospect is that, just as noted by a cartoon guide to physics here, so if it is in elastic collision, then they're supposed to stick together, move on, and in that case kinetic energy is not conserved. But if it's elastic, the major issue is that kinetic energy is conserved and then their final velocity is not the same. So here in this question on heat, we are told that a calorimeter containing 65 grams of ice at minus 10 degrees Celsius is heated uniformly until it boils after 180 seconds. Our mandate is to sketch a labeled graph to illustrate the variation of temperature of the ice with respect to time. So we have our graph here, and what inherently we are being asked is that what is going to be the stages that the ice at minus 10 degrees Celsius is going to pass through from the state in which it is ice to the state in which it boils and vaporizes at 180 seconds. So if we are to look at that, this is just a very good denotation of what we can get, and I've just noted the number of points here. Now from minus 10 to 0, taking its temperature from minus 10 degrees Celsius to 0 degrees Celsius, initially it was ice, but now it's being converted, is melting, okay? And now when it gets to 0 degrees Celsius, what is going to happen is that at that constant temperature, some time is going to elapse in which that particular ice is going to be liquefied. And then once it has turned completely to water, it will increase in temperature until it gets to the boiling point of water, which is 100 degrees Celsius. Then after then, it's just going to be maintaining that 100 degrees Celsius, but vaporization is going to be occurring. So this is actually the graph that we are asked to construct. In this question, we are told that a 40 Celsius thermometer reads 5 degrees Celsius at the melting point of pure ice and at 12 degrees Celsius at the boiling point of water at normal pressure. So that's quite interesting. Both the upper and lower readings are quite wrong. Our mandate is to calculate the correct temperature reading when it reads 40 degrees Celsius, and then we're also to check the temperature at which its reading will be exactly the same as the correct temperature reading, okay? No problem. So if we are to look at something like our thermometer here, and with information that we are given that is reading 5 degrees Celsius at melting point, we know that melting point originally is 0 degrees Celsius. So we can denote it that yes, when it's reading 5 degrees Celsius, it's actually supposed to read 0 degrees Celsius. Quite good to note that. And it's also reading 95 degrees Celsius at the boiling point of water. So we know that the boiling point of water is supposed to be 100 degrees Celsius. So this is the reading of the 40 thermometer, and this is the original reading that is supposed to be reading. But we're also noting, first and foremost, they say that we have to get the correct temperature when it reads 40 degrees Celsius. So that's why we are calling that X. And what we just need to do in this particular case is just to look at a graded difference and try and cross multiply. Like here, this scale here, we'll just relate it to the scale on the right hand side. So I want to take, for me, I love taking the difference, okay, from the unknown to the base, and then from the maximum to the lowest. So I can say X minus 0 over 100 minus 0. So I'm taking this minus 0 first, then I'm saying 100 also minus 0. So the same thing I also do to the reading of the thermometer, that this is equal to the corresponding value for X will be 40 minus the lower limit now is 5 over 95, which is the upper limit, minus still that same lower limit 5. So I can say from here I just have X over 100 is equal to 40 minus 5 is 35, 95 minus 5, that is 90. So I can cross multiply in this particular case to say X is going to be 35 times 100 divided by 90. Okay, so if I bring in my calculator for that, 35 times 100 divided by 90. So this is 38.8. The bar means that is a repeated value. So I can just say we have 38.89 degrees Celsius as the value of X, which is the reading when the thermometer is reading 40 degrees Celsius. So that is the very first thing we're asked to find. In the second case, we're asked to look at the temperature at which the reading will be exactly the same as the correct temperature reading. So let me just say I'm assuming that in that case what I'm going to have is something like a value, this is Y, and here the value is also Y. Okay, so just like I did there, I can say this particular reading minus the lower limit over 100 minus the lower limit. In this case, the same Y minus the lower limit over 95 minus the lower limit. So that's what I would just like to do now, to say here I'm looking at Y minus 0 over 100 minus 0 is equal to Y minus 5 over 95 minus 5. Okay, so I can say what that means is we have Y over 100 is equal to Y minus 5 over 95 minus 5 is 90. So easily I can say I want to cross multiply this, that 90Y is equal to 100 times Y is 100Y, 100 times minus 5 is minus 500, such that if I rearrange, I'm going to have 100Y minus 90Y is equal to 500, and that means that 100 minus 90 is 10Y is equal to 500. Then dividing both sides by 10, that means that inherently this 10 will cut this 10, and then Y that I'm looking for will be 500 over 10, which is 50 degrees Celsius. Okay, so the midpoint is still the same, and then the temperature which the thermometer will be reading, and then which is also the correct temperature for this particular case, is 50 degrees Celsius. All right. Here in this question, we are being asked to state Snell's law of refraction. We're also being asked that why does a musical note of the same amplitude and frequency being played on a flute, guitar, and trumpet sounds different? So for the solution to this, we'll look at to say that Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media, and that ratio is what we actually call the refractive index. Okay. On the other hand, musical notes is of different sound in different musical instruments due to the presence of notes that are various frequencies that are produced along with the fundamental frequency, or we can say that it's because of the overtones or harmonics of different, or maybe we can say higher frequencies or pitch of the higher frequencies that are being produced. Okay, so the fundamental frequencies are there, but then the overtones, the subsequent ones that will be building on it, they're actually going to be overtones, and then they will have different pitches. That's why sound will sound different in a flute, guitar, and trumpet as compared to one another. Here in this question, we're being mandated to look at similarity and differences between a camera and the human eye. So if you want to look at it, for the similarities, both of them use converging lens and both of them are sensitive to light. And then for the formation of the image on both the eye and the camera, the formation of the images are normally inverted. Okay, and now for the differences, the camera has a fixed focal length, but the human eye can actually have varied focal length. You can actually tend to tint your eye or maybe focus more, so that will just a little bit affect the focal length that you are going to actually form eventually. Now, distance between the film and lens can be varied, but the distance between the lens and the retina is fixed. There's no way you can change it. It's there and it is as good as it comes. Then of course the camera is a mechanical device, while the human eye is actually a natural organ. All right. So here in this question, we are being told that a light ray traveled from water into the air at an angle of incidence of 30 degrees, and we are to calculate the speed of that light ray in water and the angle of refraction in the air. Okay, very good. But we need to note some peculiarities to this question. We are told that the light ray is traveling from water, so this is water, okay, and then it's traveling to the air. So that is what we are given. And then we have to find the speed in water. So speed in water we are looking for. We have to find the angle of refraction in the air, R in the air. That's also another thing that we are looking for. As a rule of thumb, we should know that the refractive index is actually given as the speed in air as a ratio of the speed in the medium we are considering. Here, the medium is water. So refractive index of water is actually the speed of the light ray in air over the speed of the light ray in water. So since we have been given that n to be 1.33, and then we have the speed of that light ray in air to be 3 exponent 8 meters per second, we can find the speed in water to be the speed in air over that refractive index. So that will be 3 times 10 raised to the power 8 meters per second divided by 1.33. So to say I have 3 exponent 8 divided by 1.33. So this is, let me put this in standard form. Okay, so it's exponent 6. If I want to move this point in two places, I can say 1, 2. So this will be exponent 8. So it will be 2.25. But I have this 5, so it has to be rounded up to 1 and added to the initial 5. So that's 2.26 exponent 8. So this is 2.26 exponent 8 meters per second as the speed of the light ray in water. So that is the first solution that we need to get. In the second case, we are going to have to look for the angle of refraction in the air. So we can make use of sine I over sine R. But now sine I over sine R will have to be the refractive index in the air, which is generally unitary, okay, over the refractive index in water. So now we are doing like this because we are moving from water to air. That's why we need to reverse this particular refractive index. Initially, originally that the refractive index of air over the refractive index of water. But since the refractive index of air is just 1, we are good and fine like this. So that if we cross multiply, if we have to cross multiply here, we are looking for sine R. We already have sine I. We can say sine R is equal to n sine I. So that sine R means the angle of refraction in the air that we are looking for is equal to n, which is 1.33 multiplied by sine I. Sine I is sine 30. Sine 30 is actually 0.5. So this is 0.665. Okay, so R will be the arc sine of 0.665. Okay, so you can use our calculator. Arc sine 0.665. What's that going to give us? 41.682. You can just say 41.68. This is 41.68 degrees. So our understanding of the fact that this particular ray of light is moving from water to air had helped us to holistically solve this question to find the speed in water and then the angle of refraction in the air. Here in this question, we have to state the mathematical representation of the Newton's law of gravitation. So notice what we are being asked. They are saying what they are interested in, nothing but the mathematical representation. So you just need to write out the formula for that Newton's law of gravitation, that the force of attraction between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. Now the r is the distance between those two bodies, the masses are m1 and m2, and g is the gravitational constant. So once you just write out this, that is as good as it gets. Your full mark is assured. I'm just including this as a pictorial view for you to understand what we are talking about in this case. Here in this question, we're being asked that how is a compass needle used to draw magnetic lines of force around a bar magnet. Now, students, you just need to be able to capture this effectively. In the first place, you need to place the magnet and compass on a plane sheet. So here we have the magnet, we have the plane sheet, they are placed together, okay? And then you have to adjust the position of the compass until the needle is pointing away from the magnet, and you mark the position of the head and tail of the needle. So this is what we are talking about here. So if you put the compass here initially, you can see that the pointer is pointing towards the magnet. So we don't want to start from there. We want to start in a position in which that needle will be pointing away from the magnet, and so this here is that particular position, okay? And once you get that, you are going to move the compass to another further point from the magnet. Then you also mark the needle position in that location. So that's why we're having something like this here again, okay? And then just repeat the procedure here, you repeat the procedure here, you repeat the procedure here, until you are seeing the pointer also touching the magnet in this particular last case. So after doing all of those, what is left is for you to join all those marks, all those arrows that we have actually drawn, the one shown in blue here, okay? You just join them with a line. So this is like that line we're talking about, and then we would have drawn one magnetic line of force. Then you just repeat the process, do another one, and that is how it's just being done. Now this is how it's being postulated that whenever you see a magnet and you are seeing lines of forces drawn from the north to the south pole, is an assumption that yes, we've done this and we have gotten those magnetic lines as acting in that direction. So experimentally you can also do that, and this is what you are going to get in that case. All right, a good question for us to consider here is that we should distinguish between series and parallel combinations of resistors. So this is just a table highlighting those differences, and this is a diagram that is also depicting here in the first case the resistances in series, and here the resistances in parallel. For the resistors in series, the voltage across each resistor is different because it is current that is the same in a series circuit, okay? But voltage across each resistive load is going to be different. So we have V1 for R1 and V2 for R2. However, in a parallel setup, it's the same voltage that is flowing across loads in parallel. Resistors in parallel will carry the same voltage. So V across R2 is also equal to V across R1, okay? So for the current that is flowing, same current is going to flow across each resistor in a series circuit. However, when you are looking at a parallel circuit, the current will be different. So that's why we have I1 and I2, okay? Now, in a series circuit, the effective resistance is the sum of the individual resistances. So in this case, R total is going to be R1 plus R2 for the series setup. But in this particular case, it is the inverse. The effective resistance we are going to have here, 1 over R total is equal to 1 over R1 plus 1 over R2. So if you want to find the LCM, you can say what you are going to be having is something like 1 over R total is equal to, LCM will be R1, R2. Then if you just factor, this will be R2 plus R1, so that your R total will be the inverse of that, it is R1, R2 divided by R1 plus R2, okay? And then finally, the effective resistance in a series circuit is going to be greater than the parallel arrangement of resistors. So R total here is actually greater than this R total, okay? So these are just the differences between series and parallel combinations of resistors, and if you are able to think 3 points, if you are able to raise them effectively, that should be good and fine to earn you your full marks as requested in this question. Here we are being told that a current of 3 amperes passes through a heating coil of length 65.2 centimeters, which has a cross-sectional area of 3.2 millimeter square. So students, first and foremost, I want you to just note insight into what you are being given. Here the length is given in centimeters, the cross-sectional area is given in millimeter square. So those are not the same, but we need to be consistent with our unit, okay? And then this particular heating coil have a resistance of 3.5 ohms. If the current passes through the coil for 5 minutes, again, that is in minutes, we need to convert to seconds. If we are going to be using that, we have to calculate the resistivity of the coil and the energy that is dissipated by the coil. So this is a pictorial view of what we are having. And then for me, I would just like to first and foremost convert all the units. Here we have 65.2 centimeters, and that will be 65.2 times 10 raised to power minus 2 meters. So that's going to give me 0.652 meters. Okay, so this is the length of the heating coil. The cross-sectional area we're given as 3.2 millimeters square. Now you need to be careful. We're talking about millimeter, but not just millimeter. We're talking about area. So it's the square of the millimeter. So for us to convert, we need to say this is nothing but 3.2. Okay. If it is just a singular millimeter, we would have said times 10 raised to power minus 3. But because we are squaring it, so we also need to square this. So this is nothing but 3.2 times 10 raised to power minus 6 meters square. So that is what we need to note so that we don't make mistake in this particular case. So we are giving the resistance to be 3.5 ohms. That's good. And then we are giving the time in which the current is passing through it to be 5 minutes. That will be 5 times 60 seconds, which is 300 seconds. So we can now go ahead to try and find the resistivity of a coil. Generally, resistance of a conductor is given as resistivity multiplied by length over the cross-sectional area, such that from here we can find our resistivity to be the resistance multiplied by the area divided by the length of that particular conductor. So if you want to put in all the parameters, we have resistance, we have the area, we have the length, we can say our resistivity in this case is going to be, the resistance is 3.5 ohms multiplied by the area, that's 3.2 times 10 raised to power minus 6 meters square, over the length. The length is 0.652 meters. So we can just get this. We can use our calculator to evaluate this, that we have 3.5 times 3.2 exponent minus 6 divided by 0.652. So what's that going to give us? So this is 0. Okay, let me just put that in 17.18, or if I just move this again, 1.72 exponent minus 5. Okay, so this is 1.72 exponent minus 5, and what's going to be the unit? It will be ohm. Now this meter would have cut this meter to remain only 1 m here, so it is ohm meter. All right, so that is the resistivity of this particular heating coil. Okay, so in the second case, we are asked to find the energy dissipated by the coil. Energy for this particular case we can find by saying it is the product of the current multiplied by the voltage multiplied by time. And if you look at all of those, okay, we don't have the voltage, but we know that voltage is IR. So here it will just be I square R multiplied by T. So our I, it is 3, we have 3 square. Our R is 3.5, okay. Our T is 300 seconds. So you just need to find this on the calculator to say we are having 9 multiplied by 3.5 multiplied by 300. Okay, so this is 9450. So this is going to be 9450 joules as the energy dissipated, and we have gotten the resistivity of the coil initially. In this question, we are asked to define viscosity, and we are also asked to state 2 fundamental assumptions of the molecular theory of matter. Here is the solution to this question. The viscosity is the internal friction that exists between the layers of molecules of fluids, whether it be liquid or gas. So that is what we actually allow sometimes maybe a pond skater to actually be on the surface of the water, because there is some level of viscosity on the water surface. Okay, so that is that about that. Now, for the assumptions of the molecular theory of matter, number 1, we can say that matter is made up of molecules, and those molecules are in constant rapid motion, and they also experience force of attraction. And then of course matters can exist in solid, liquid and gaseous state. So this holistically will help us to answer this question, and that will be done with that. Here we are being told that the kinetic energy of electrons that is emitted from a metal surface when light of frequency f falls on it is 4 exponent minus 19 joules. Now if h is the Planck's constant, we are to express the threshold frequency of the metal in terms of the given parameters here in the equation. So this is quite interesting. You can notice that we are not giving any value of the constant, like we are not giving h to be a particular value, and we are not giving c to be any particular value. That's why they are saying that we should express the threshold, threshold frequency in terms of the given parameter. So that's what we'll try to do in this particular case. But this pictorial view is helping us to explain it, that there is this light of frequency f, and of course the amount of that energy that's coming from the light is hf. When it is incidence on this metal, there is a kinetic energy with which electron will be emitted, and of course the metal itself has inherently a work function, and what we normally work with is that the energy hf is actually equal to the work function plus the kinetic energy in this particular case. All right, so if that is what we have, hf is the photon energy, f is what we are given as just ordinary f. We are not giving its value, but we are given that the kinetic energy that is emitted is 4 exponent minus 19 joules. So in this particular question, we can say hf, which we still have, is the work function. Now the work function itself is a product of the Planck's constant and the threshold frequency f naught. So we have it that this is hf naught plus, since we are giving the kinetic energy, we don't need to write k already. We just need to write it is 4 exponent minus 19 joules. So since we are asked to express the threshold frequency in terms of the terms, then we should make f naught the subject of the formula in this particular case. So here, if we are to rearrange, we can say hf naught is going to be, when this 4 moves to the other side, we have hf minus 4 exponent minus 19, and then f naught itself is going to be hf minus 4 exponent minus 19 divided by the Planck's constant h. And if we want to break it into its constituent terms, we can say is that f naught equals to hf over h is actually f, then minus we still have 4 exponent minus 19 divided by h. I just broke this into its 2 times, hf over h, then 4 times exponent minus 19 over h, and this is what we are going to have, and the unit is going to be at. So this is the expression for the threshold frequency of this metal in terms of the given parameters for this particular question. Here in this question, we are told that light of frequency 6.62 exponent 14 Hz is incident on the metal surface with work function 2.08 exponent minus 19 joules. Our mandate is to calculate the wavelength of the light and the energy of the light. So here in this question, we are given the Planck's constant h, and we are given the speed of light. And a typical example of what this scenario is looking like is this. We have some photon of light that is of some particular energy incident on this metal. We are looking for the wavelength, and we are looking for that energy, but we are given f. So we are given the frequency that it is 6.62 exponent 14 Hz. And then we are also given the speed of light to be 3 exponent 8 meters per second. Generally, we know that the velocity of light is given as frequency multiplied by lambda. That velocity here is c. So let me just put that what we are actually having inherently is c, and this is c is equal to frequency multiplied by lambda. So the wavelength lambda will be the speed of light over the frequency, and since we have the speed of light and frequency, we can say lambda in this case is going to be 3 times 10 raised to the power 8 over the frequency 6.62 exponent 14. So we can bring in our calculator to say 3 exponent 8 divided by 6.62 exponent 14. So this is going to give us 453 exponent minus 9. But if I move it 2 places back, if I move the decimal point 2 places back, that will be 4.53 exponent minus 7. So that's expressive enough. 4.53 exponent minus 7. And what's going to be the unit for the wavelength? It is meters. So that is as good as it gets. So this is question number 1 In question number 2, we are asked to find the energy of the light, and already we have defined that energy is actually the Planck's constant multiplied by the frequency. Do we have the frequency? Yes. Do we have the Planck's constant? Yes, we are given. So that energy is going to be nothing but the Planck's constant, H, 6.6 exponent minus 34, and the frequency 6.62 exponent 14 at. Okay, so again, our calculator will be of help to us here. We have 6.6 exponent minus 34 multiplied by 6.62 exponent 14. So please just ensure that there's no mistake. You can check and check again that you put the values correctly, and you can solve for that. That's 4.3692 exponent minus 19, or I can say 4.37. So this is 4.37 exponent minus 19. And what's going to be our unit for energy? That is joules. So this is just how we go about solving this question, and will be good and fine. Here in this question, we are asked to list 4 components of a slide projector, and this is a pictorial view of the slide projector, which is an optomechanical device. You just put in your picture slides into like this slot, and then the mechanism with which is going to work and project those images that you have inserted onto a projecting screen. So some of the components include the projection lens, okay, the slide carrier that you are going to insert your slide in, a condenser, the light source that will be beamed on those particular images, a concave mirror through which the light rays will pass, and then we also need a projector screen and co. So if you are able to just list like 4 of these, then you'll be good and you'll be fine, and the question would have been answered and dusted. Here is a question asking us how electricity is being generated from a dam. Okay, so let me just use a picture to explain this. Normally, as simple as it gets, just for you to answer the question, you can say that the dam water will pass or fall through a narrow opening of the dam, and it will rotate a turbine. The turbine in turn will rotate the dynamo which generates electricity. If you are able to state that, that is good. But for me, I used to say this: a picture is worth 1,000 words. So here, this is the reservoir. Okay, let me use ink, red ink. So this is the reservoir. Okay, and this is the dam. The water has been stopped initially. So if you want to actually start generating electricity, the water inlet will ask to pass through this penstock, and then that water, as it is flowing, it will be turning this particular turbine, and the turbine itself will just rotate the dynamo that will go ahead to generate electricity, which can now be passed through the transformer and then connected to the transmission lines and distributed to wherever it is that it is to be distributed to. So this is just as good as it gets. If you are able to just state these 2 statements, it will be good and fine and earn your full marks. Here in this question, we are to contrast a wet Leclanche cell and the lead acid accumulator. So here is the tabulated differences. If you want to compare, maybe any 2 or 3 will be sufficient. In a wet Leclanche cell, you will notice that it is just a primary cell, whereas the accumulator cell is a secondary cell. The positive terminal of the Leclanche cell is carbon rod, but the positive terminal for the accumulator cell is lead peroxide. Okay, the negative terminal of the Leclanche cell is zinc rod, but the negative terminal of the accumulator cell is lead. Now, the Leclanche cell cannot be recharged, whereas the accumulator cell can be recharged and reused. And for the Leclanche cell, the current only lasts for a short time, but for the accumulator cell, since it is a secondary cell, the current will last for a long time, and then even the durability definitely will last far more longer. So you can find that as being used in your motor vehicle because it is being recharged and the current can last for a long time. And here we are being told that a load of 200 kg is raised through a height of 6 meters in 4 seconds. We are to calculate the time rate of energy that is used in horsepower. Okay, so if you want to have a pictorial view of what we are talking about, it's just something like this here, in which we have that load 200 kg as a mass. So here, this is the mass. Okay, then 6 meters, this is the height, and then the time that was taken is actually 4 seconds. We are to calculate the time rate of energy that is used in horsepower. We are giving G to be 10 meters per second square and 1 horsepower to be 746 watts. So what is the formula for the time rate of energy? Look at what they are saying. They say the time rate of energy. That means we're actually talking about power. Okay, it's power, it's not energy. So you can see that for this particular case, the power is going to be mgh over t. That's just energy over time. And since it is an object being raised through some height, so this will be good and fine. So if you want to put in those parameters, that power will be the mass, which is 200 kilograms, multiplied by the acceleration due to gravity, 10, multiplied by the height, which is 6 meters, divided by the time, that is 4 seconds. So you can say 4 year 1, 4 in 20, that is 50. So we have 500 times 6. 400 times 6, that is 3000 watts. Okay, but now look at what we are given. We are being asked to find it in horsepower. We are given that 1 horsepower is equal to 746 watts, but now we have this 3000 watts, but we are looking for the equivalent amount of horsepower. We can call that x, and with x, if we cross multiply here, we will see that x will be 3000 divided by 746. So we can use our calculator to evaluate that. We have 3000 divided by 746. So what's this? This is 4.02. So this is nothing but 4.02 horsepower as the time rate of energy of this particular system. All right. And so with that, we have come to the end of this video, and it has been a very wonderful journey in which we took our time to look at all of the 17 questions NECO is really trying. 17 questions for the exam. Well, of course, you need to pick some questions. It's not that you answer all, you answer some, they specify in the exam. And then I believe that with this, you have been able to get some better insight into these questions. You'll be able to answer them correctly if you are facing them in your exam. And all of these are done in a bit to prepare you for excellence. So if you just want some more videos, you can check our playlist. We have quite a whole lot of resources in physics, in mathematics, and even in chemistry that can help you to build excellence in your academics. And we want to trust that, God willing, that will come to pass and you'll be the best that God has created it to be. Don't forget to subscribe to the channel. It's Dave Tutor Academy. And until next time, God bless you.